Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we will finish discussing data models. Give you a few seconds to get ready. So we started looking into data models, in particular trees, because tables you already know from the bachelor's level, and graphs and cubes we'll worry about later. And we basically noticed that XML and JSON, and actually many other models like YAML, are in fact trees, or more exactly collections of trees. And so when you denormalize a table, you get a collection of trees. And collection of trees are going to be of interest to us in the coming weeks. We'll go all the way to document stores, MongoDB, and so on, but we are just building things step by step, right? So we saw that you can actually literally draw a tree, computer science tree, of course, when you have an XML or JSON document, and there are several data models like the XML info set for drawing XML trees. JSON has an implicit data model, but it's also typically extended by validation languages that typically also provide an extension of the data model. So we basically left with schema validation, which allows you, in addition to well-formedness, so once you have noticed that a document is well-formed and you parsed it into a tree representation in memory, you can ask the question, does it fulfill my structure that the schema specified? So you remember that you have here a schema that I put at the bottom, and then the documents called the instance on the top, and you ask, is it valid against this? So here, that language was designed for pedagogical purposes because it's very visual. So you see immediately that here you have an object that has R that is a key associated with an array of objects that have a key foo associated with a Boolean. And you can see that this here is valid against this. So this is the compact syntax of JSON, and it is made in such a way that the schema looks very close to the instance. So if you look at the schema, you should immediately understand the structure that the instances have, okay? So now I left here with the fact that by default, extra fields are forbidden in JSON. So for example, if you have here last and first, and you have last and first in the instance, you cannot add another field here that wouldn't be already in the schema, right? But the nice thing about making schema validation optional and having more flexible schema languages is that you can add in your schema that you're totally fine with extra fields that you don't know in advance. However, since it's an advanced feature that requires another flavor of JSON, but you don't need to worry too much about it. I'm just telling you it exists. So there is this more verbose syntax that says that basically we expect an object, base type is object, and the content has basically pairs that have the key is last and the type is string, the key is first, the type is string. And with that syntax, you can actually add some property here that say closed is false. So the difference between the two syntaxes is that in this syntax, this is actually good to be aware of this kind of design when you design your own data. We call this dynamic. So the schema language is dynamic because the keys that we put in the schema can be absolutely anything. These are basically the names of the keys that you want to give here, right? This here is a more static schema language in the sense that the keys in the schema, right? I'm really talking about the keys in the schema are actually defined in advance. There's a key called kinds that says if it's an object, an array, an atomic, a key that is the base type, we can define subtypes, a key that's called contents, and for the pairs, the key is always called name associated with the key of the instance, and that it's always called type. So it's static because here it forces you in every schema that uses this verbose syntax to have exactly these properties here. Okay, as opposed to this one where you can really put anything in there. So there's two kinds of ways to design such a schema language. But the benefit of using a static syntax like this is that it's fully extensible, it's more verbose, but then you can do many more things. So the goal was that this compact syntax here covers the 80% of easy use cases, like the exclamation mark for required and so on, just easy and visual. And for the 20% of advanced feature, you would just move over to the verbose syntax. But you don't need to learn it, right? The verbose syntax, you really don't need to worry about. I just wanted to tell you that you can do more things. And in particular, in the verbose syntax, you can add closed, which if you set it to false, then it's open. And then you allow in the instance for any additional keys, even though they are not listed in here, right? Who is with me? Okay. So now, if we recap what we've seen on JSON. So what is general about many of these schema languages is what we can do. For example, in a schema language, we can restrict values to have a specific type. For example, is there a question? Let's go to your question.
I just wanted to ask if it's possible to intermingle the advanced syntax and the normal syntax for schemas. Like, can you have an advanced object within a normal object?
In theory, yes, you could. It's just the design when you do that becomes very difficult to learn basically when you mix. So I'm taking your question as a meta question, right? It's not just about JSON. It's about like any language that you want to define in JSON, schema language. It's usually a good idea to either say, okay, that's static or that's dynamic. But if you go for static, then try to make everything static, right? Having said that, not everybody does that. And in fact, if you look at JSON schema that we are going to study later, JSON schema mixes the two. It has a part that is static, but then some other parts that are dynamic. It's okay. I mean, you can do it, but you just have to take into account that it can be confusing for users. Does it answer your question?
Yes, thank you.
Yeah. So this is, since you asked this question, I can talk a little bit about that. This is really the design. If we wanted, we could have made that part dynamic, right? Instead of having an array and really explicitly having name and type, we could have made that part dynamic, saying instead of that array, we would have an object that's last colon string and first colon string, right? But again, that would have been confusing because then that would be intermingling with what would be the compact syntax. So this is why we consciously kept it static in this way. Okay, but that's already an advanced question, right? That's, yeah, over here.
I would like to ask, why do you make a default that fields are optional and also that there cannot be extra fields? Because I would seem more natural to do it the other way around, that I want this field to be present. And if there is something extra, I don't care.
This is a very good question. And in fact, this is indeed a design question. So when you design a schema language, that's a question that you answer in every schema language. And there is no right or wrong answer. For example, you will see in a JSON schema that I think it's open by default in JSON schema, and then you close it, meaning you don't accept extra fields explicitly, right? But the default in JSON schema is that extra fields are fine. In JSON, it's the opposite. Again, there's no right or wrong. It's really a design decision. The same for required. Whether or not you require a field by default or you make it optional by default is a design decision, and there is no right or wrong, right? And so that's the sort of things that if you have to remember something, you know, I teach you with all these examples and so on, but what I want you to learn is really the high-level considerations of schema validation. So even though here it happens to be optional by default and closed by default, just remember that it's a switch, that in any schema language can be the one, can be the other. You just look up the documentation, right? And you see what the documentation says. Now, I can say a few words about why we did it in this way. That will actually become clear later when I show you the data frames, the fact that you can actually draw these as data frames. Because if this is what the compact syntax does, that it doesn't allow extra fields, that basically allows you to transform a JSON schema to a data frame schema, like the ones you can have in Spark and in Pandas. So that is the motivation for not allowing extra fields. Because in a data frame schema, you do not allow extra fields. You have to specify all of your columns in the data frame. So this is something you will see a bit later, and normally that should add up, and that will make it clear why we made this decision. Okay?
Thank you.
All right. But again, there's no right or wrong. Just it's a switch, and either decision is totally fine. Okay. So I was here. So this would be the dynamic compact syntax. It would be the static verbose syntax. That's more powerful. So what can we do in a schema language, any schema language? you can restrict values to a specific type. You can say the value associated with the key must be a string, or it must be a Boolean, or it must be an array of integers. So that's the feature number one that schema validation languages allow you to do. Some other feature that is very common to schema languages is an implicit cast. That is technically not part of the validation, but of the annotation, because the cast actually is about what you have in memory after the validation. Because you might have before the validation, you might have a string that contains a date, but after you have validated as a date, in the memory, you will have replaced it with an actual date, with an actual instance of a date class, if you do it, for example, in Java. So this is called annotating, and it means that you cast. So I took the example of a date, but this is also true with integers, with basically any types, that in the memory, once you have validated with a specific type, you cast the value to this type. And this is the reason I told you, for whatever we have in memory before the validation, we don't care if it's quoted or not quoted. We just look at lexical values, the literal value. So we don't care if there's quote or not quotes. We take it as a lexical value. We see, okay, does that lexical value belong to that type? If yes, then you pass the lexical value and convert it to an actual value of that type, right? So this is why here you basically look at it from a lexical value perspective. This is the lexical value 2134. Doesn't matter if it has quotes or not. You could also do it without quotes, but you look at the lexical value. And after that, if you validate it as an integer, then you have an actual integer in the memory. All right, feature number 3 is you can require a value or make a value optional. So you can say this key is mandatory or this key is not mandatory, right? And what is the default, that's yet another design question, but you have control over that when you build a schema. Then you have control over allowing or not extra fields. The schema language TPQ gives you control of that. And again, what the default is an open decision. You just need to look it up in the documentation of the language, right? So basically what you see here was the answer to the question you've just asked, right? That the schema language might make the one or the other the defaults. Okay, what else do we have? Oh, default values. So that I haven't shown you. But in fact, what you can also say in a schema is that if a key is not present in the instance, you can just add it with a default value. This shouldn't surprise you. You can do it in SQL, right? In SQL, you can also specify the default value of a column. That you can also do that. So that you can do in a schema. Again, that would be part of the annotation. And after the validation and the annotation in the memory, you will have the default value that has been added to the object. And finally, and that I didn't show you, but you can also specify primary keys. For example, if you have an array of objects, then typically a schema language could allow you to say that you want foo in that array of objects, because remember, an array of objects is a nested table, right? So you could say foo is my primary key, and then it will also check that you don't have twice the same primary key within that array of objects. For whom is that clear? Right? So of course, I'm not showing you how to do it. I'm just saying you it's possible, right? In many schema languages, you can do these sort of things. So you see, these are all the sort of things you can do with schema languages, any of them. Then you can learn plenty of them. Look at the documentation, they're really all the same. So just for the sake of showing to you, I will show you JSON schema, right? You will see it's the same features. But before we do that, I wanted to show you for the Great Language Game, which is a data set I told you about with 16 million objects that look like this, this would be the schema. You see how visual it is? It looks the same, right? Guess is a string, target is a string, sample is a hex binary. That's basically a base 16 representation of a sequence of bits. Choices is an array of strings. You see an array of strings, and you see all these exclamation marks here that basically require the key to be present, right? So who agrees and sees that the instance on the top is valid against the schema at the bottom? All right, very good. So this is the idea. And basically, it's very straightforward if you take an instance document to turn it into a JSON schema in the compat syntax, because you really just replace the values with the names of the types. That's pretty much all you need to do. Then you put your exclamation marks where you want to enforce requiring a key. Here's another example. I told you this one is pretty easy to turn into a schema, right? So imagine you have billions of documents that look like this with variations on that. If we build the schema, again, I told you, you just replace the values with the types. Do you see that this would be the schema? Who sees that? All right, it looks very much like it, right? You see just exclamation mark to require it. A is an integer, B is a Boolean, C is an array of objects, and inside these objects, we have foo and bar. Foo is a string, bar is an array of strings, and you see here, foo is required, it's everywhere. Bar is absent from the third object here. So in the schema, if we want this to pass the validation, we have to make bar optional. So this is here, I didn't put an exclamation mark to not require it. Okay, so it means that now you can take this schema and validate similar objects. We have another question.
So if you asked us to provide a schema for a given object, should we by default assume that it's required unless we have an instance where it's not?
It's really based on reality, right? When you do it, typically you have a use case in reality. If you see that you have billions of objects and they all have the key, then it's a good idea to make it required, because you can assume if you have billions of that, it's going to be required. If you see that it's not always there, then you make it optional. But it's a good idea to make it required. Now, again, in reality, it might not be that simple. Maybe in reality, you're designing the schema before you see the data. So here you have to ask yourself, okay, what about the people who are going to create the data? Will it be in their way if I make it required? You know how it is with the administration, right? You have to fill a form, and if you don't fill it entirely, then it bounces back to you. This is the sort of things that arrive, basically, if you make a field required. This is a real life thing. But at the exam, of course, if we ask for validity, it can be required or optional. In both cases, it's going to be valid, right, if the field is there. Okay, thank you. All right, okay. So now that I've shown you the features of a schema language, let's move on to JSON schema, which is another one, but you'll see it has the same features, just looks different. So here we go. So as always, the instance is on the top, the schema is below, except that now it's no longer JSON, it's JSON schema, right? And this one is actually used at a lot of places, so you will probably see it. Now, how do we say that we make that valid? We want a key called last associated with a string, and that's how we do it. Now, coming back to your question about static versus dynamic, let's look closely at what they did here in JSON schema. You see that part, type properties, is static, right? Type and properties, they will always be here in all the schemas. That will be type and properties, and you just changed the type that you want and the properties that you want. Now, do you see that part is dynamic? That part is dynamic because here, what you put in here when you create your schema will depend on what you want here, right? So who sees that is static and that is dynamic, right? Okay, fabulous. That is static, that's always type, and then you put the string in there. So really the difference between static and dynamic is that when it's static, the keys are kind of hardwired in the schema language, and you would just change the values. When it's dynamic, then when you design a schema, you're also allowed to make up the keys that you want. Okay? So that basically says that you have something that is an object, and the properties, property is just a synonym for key in JSON. So the properties are last, which is of type string. Now you see the recursion, just the same kind of recursion we have in JSON. So we have here this object here, that's the outer level, and here that's an inner level, always with the type property. Yes?
Why is there a top level type? Isn't that always an object?
It doesn't have to be, because for example, here it's a string, right? Type string. So it can be type object, type string, type array, type anything you want. But here in that case, we validate an object, right? But you could also maybe validate an array instead. Then you would have type array.
But isn't the top level JSON element always an object?
That is also one of the things that gets you a troll on internet forums. So let me add this one as the third way to troll an internet forum. You ask exactly that. So in practice, if you look at many document stores, then yes, the top level is going to be an object. I mean, this is common practice. Now, if you look at many of the specifications, it doesn't actually enforce that. So technically, you could have any JSON value at the top level. So you can imagine a JSON lines document where you have a mixture of arrays and objects and even strings or numbers just by themselves on the top level, right? So it really depends on the system you're looking at. JSON is generic enough to allow that. But for example, if you look at MongoDB, then in MongoDB, that has to be an object at the top level, right? And we'll see that the reason why we like to have objects at the top level in many technologies is that this maps very well to data frames. And that I will come back to again, right? And then you'll see why it makes sense to require objects at the top level, right? Does it answer your question? Awesome. So now, okay, so let me add a field. So here you see in the dynamic part, you can just add a second key that has the intended name, and then it is of type string as well. By default, it's optional. So that's like JSON. So here they decided that it's allowed to not have a key. So the way that you read the schema is basically, if there is a key called first, then it should have the type string. But if there is no key called first, then that's fine too, right? This is what it means. So this instance would be valid against that schema because first is optional. If you want to make some of them required, you do so with a static property of the schema. Again, it's static because it's always called required. It's always called that way, containing the list of the keys here that you want to require. And here you say last and first would be required. In JSON, that would be the exclamation mark in front. In JSON schema, that's basically in the required field. So you see JSON schema uses a bit of a mix of compact and verbose and a mix of dynamic and static. Okay. Then what about extra fields? Well, it turns out that in JSON schema, they made the opposite decision than we did in JSON. So in JSON schema, it's the opposite. If you can absolutely have any extra fields you want, if the schema doesn't explicitly forbid them. So this is fine, totally fine. And if you want to forbid it, you just had this static property because it's always called additional properties, which is false. And then it means it disallows additional properties. So here that would be valid. That would no longer be valid if you add additional properties false. Who is with me? All right. There is no right or wrong. Just read the documentation of the schema language and you will see whatever is the default. Do we have a question?
Yes. How do we define required fields if they were nested in other objects? Do all the keys need to be unique?
Then you would do it in the nested object. So basically, this is a recursive structure. What you have here, that is basically specifying the schema of an object, works recursively too. You could, for example, copy-paste that inside this and have a nested object here. Then you would put the required inside in the nested object type. Does it make sense? Yes. Awesome, perfect. All right, okay. So they really see it as a recursion. All right, now in JSON schema, you can also change the types, but the list of the menu on the menu is not that long compared to JSON. So JSON has this huge list of types. In JSON schema, it's a bit limited. So you basically have string, number, Boolean, null, array, object, but nothing much beyond that. It might have also an extra type, I think maybe for some kinds of numbers, it might have integer, I'm not sure. But basically, it's a very short list of types. If you want more specific kinds of types, you have to do it with what is called a format. Like a date is basically a formatted string that looks like a date. So it's a bit less flexible in terms of the type system, but this is the way that it works, right? So you have string, number, Boolean. So you can see that it means that JSON schema was designed very closely to the JSON syntax, because in the JSON syntax, you have string, number, Boolean, null as atomics. So this closely matches the JSON syntax and null, right? So you have the four, string, number, Boolean, null. Okay. Now, and here, this is the part where you cannot guess it. You have to look at the documentation. How do you allow any value, what we called item? So there is a special type called item in JSON and in JSONic, actually. But in JSON schema, there isn't any such type. So what you do is that you use the Boolean true. So it looks a little bit like it fell from the sky, but this is how it is, right? If you put true instead of the what's called the type descriptor, instead of that you put true, that means anything. It allows for absolutely anything. So here you can put whatever you want inside of location because it said true, all right? And false would forbid it. So false would basically mean you are not allowed to even have a key that is called location. False means it will always fail the validation. Yes?
Could you go back to the null slide?
Yep.
So when we say it's type null,
yep.
So every value has to be null there.
Exactly, because that's a type that only has one value and that value is null.
So it's basically checking whether the whole, let's say, column is null.
Yes, exactly. So that I will come back when I describe the data frames, but basically nulls, there are several ways to handle them. You can consider that null is the same thing as an absence of value, which MongoDB is doing, or you can consider that null is a specific value that belongs to a type, a singleton type actually, just like Boolean has two values, null has only one. So there's the two ways of doing that. In JSON schema, they make a distinction between the value null and the absence of value. And because they make that distinction, they have to define a type called null, and the only value that is permissible in that system is null. Okay? Any other question? Yes, over here.
So JavaScript has this value undefined, which in many cases is like if you access into an object with a field that it hasn't defined, it'll give you undefined. Is this a valid value that you can have in JSON? Is it treated in that same way?
Aha, undefined. So there is no concept of undefined in JSON or in JSON validation languages. There is no concept of undefined. There is just null or absent. That's the only two things you have. Now, the concept of undefined, if you think of it, what it means, it basically is in programming languages. For example, in Java or in C++, you can basically create a variable, but without initializing it, right? You declare a variable. In some languages, it means the value will be whatever happened to be in memory at that location. That can actually be a cybersecurity risk. Or it could just say it's undefined if you haven't yet initialized it, right? But it is really something that has to do with programming languages more than with data modeling. Now, if you want to capture the semantics of something that you don't know the value of, then what a data modeler would say is they use null for that purpose. So for example, in a PostgreSQL or in a relational database system, you could say, okay, I'm putting a null in there if the value is unknown or undefined. But this here is not something that would be inside the database system. That would be something that the users of the database system decide. So whoever makes the schema would write in the documentation of the schema that they intend for null to have this and that meaning. Does it make sense?
Yeah. I also wanted to ask, JavaScript doesn't distinguish between integers and floating point numbers. Is there ever a case where, say, if you're transferring from data to a relational database where you actually do care about that kind of thing, is there kind of a gap there where JSON doesn't have a required feature?
So here I can also say a few words about that, about the number type system. So I would like for you to understand it from a formal perspective. There is basically the formal perspective, and then there is the implementation perspective. So what happens with if you want to do it rigorously with types, and the way it's done in XML schema and in JSONic, is you basically have a value space that contains all decimal numbers that can be written in base 10 as a finite sequence of digits. And then many of the types are subtypes of that. For example, integer with any precision is a subtype of decimal. Int is a subtype of integer, byte is a subtype of int, and so on and so on. You can have non-negative integer, positive integer, and so on. So you have a whole type system, but everything resides on the mapping between the lexical values and the mathematical values, the actual typed values. For example, the 42, which is a lexical value, and the number 42 in base 10. So this is how formally it is done. There are a few exceptions with doubles. Doubles are typically in XML schema a type of their own, it's called the type double, but it's not in any relationship with decimal. And in the lexical value space of double, you would accept the scientific notations, which you typically do not do for decimals. So whenever you have an exponent, it's basically going to be in the lexical space of double. Now, what happens when you open a JSON file and you validate it involves a mapping to the host language that you are using. Because you might be using JSON schema or JSON or XML schema or whatever language inside a programming language. That programming language could be Python, could be Java, could be C++, could be R, could be Haskell, could be any programming language. And you can do that with any schema validation language. So it's completely orthogonal, the programming language you use and the validation language you use. In particular, JavaScript happens to have given birth to JSON, but JSON is really completely detached from JavaScript now. The consequence of that is that every programming language has a different type system. I told about the type system last week, right? From a general perspective. But Python doesn't have the same type system as Java, which doesn't have the same type system as C++, and so on, and which doesn't have the same type system as JavaScript. So what happens is that when you model things, and if you do it rigorously, and sadly, not everybody does that, but you're supposed to do that, the moment you use schema validation with a host language, you should do a formal mapping between the type systems. That means that it's typically a table with 2 columns that says, these are my types in Python or Java or JavaScript, and these are my types in the schema validation language, and this is how they map. If you look online, I will show you later, but Spark does that. Spark tells you, these are my data frame types, and this is what they would be like in Java if you use Java. This is what they would be like in Python if you use Python. This is what they would be like in JavaScript if you use JavaScript, right? But you really need to understand that this mapping is never one-to-one. And that's what we call an impedance mismatch, right? It's like for sound engineers when you connect the wrong wire to some loudspeakers and you basically break the loudspeaker. Database people also call that an impedance mismatch. Basically, you have to take care of that carefully. If you encounter such a thing, you have to carefully map your types, but you need to accept that there will be a mismatch. So you need to basically explain how it's done. Now, coming back to our example with numbers in the JSON syntax. So in the JSON syntax, all that is said is lexical values. That's all JSON says. JSON says a number is basically a sequence of digits, maybe a decimal period, then a sequence of digits, and optionally an E for scientific notation, followed by a plus or a minus or nothing, and then digits and so on. But if you think of it, that's only a lexical value. It doesn't tell you anything about the type. The type will be figured out by the schema language and the programming language. What is sometimes done, actually by quite a few systems, is to convert or put in the memory representation, when you parse JSON, if there is no decimal period and no E, you're going to make it an integer. If you don't support the integer with arbitrary precision, then make it a long, for example. If you see a decimal period, but there is no scientific notation, and if you support a decimal type, then make it a decimal. If there is the letter E with a scientific notation, then make it a double. That is something that is commonly done by systems, but it's not universal. You might have systems that make everything a double, for example, or you can have systems that only make it a double if it has a decimal dot or an E, and otherwise a long, right? But there is no fundamental truth to that. This is really part of the mapping that you're going to have, and you're not going to have the same mapping in Python, in JavaScript, in Java, it's going to be different. Right?
So is like NaN, like a not a number literal, a valid JSON value then?
NaN is an acceptable lexical value in the lexical space of double and float. So if you have double and float as your type I'm talking about JSONic, XML schema, and so on, not JSON schema. But then you can have NaN, and that will be accepted as valid against double or float. And the annotation in memory will be the NaN, but the NaN will be in the IEEE 754 floating point standard. Right?
Great, thank you.
Thank you. Right beside you. Yeah.
So is it possible for like a given key or a property to say it could be this type or this type? Like for last, could we say like, oh, it could be string or it could be int?
Yep, that's called the union. So I think in JSON schema, you can use an OR, Boolean logic. It's based on Boolean logic. You can use an OR. In JSON, in the verbose syntax, you can also define unions.
And I guess in JSONic, we could like do it as like a full expression or something, and write it as.
In like JSONic, you could, so basically the way to go would be to define the user-defined type in JSON, and then you could use it to annotate a variable in JSONic, right? But that's already advanced, doing that sort of things. But you can absolutely do this. Yes?
With unions, couldn't you create a situation where it's unsure which type actually to match to? So let's say you have a union of string and float, and then you have the string NaN. What's the type of that?
So typically what happens, this is already a programming language question, right? So we will only get to that in a couple of weeks. Here, you need to distinguish between the type annotations for variables that are basically the expected type of a variable at runtime and the actual type of the value that you have in there. And technically, in the type system and in the data model of this language, which is W3C standard, the type system, what happens is that an atomic value bears its type. It has a value and a type, right? So if you would basically have unambiguously NaN either as a float or as a string. But now comes the next question in a natural way, which is what is when you validate? Meaning that in your instance, you have the string NaN, and then the expected type is a union, then you have an ambiguity. You have an ambiguity. And so what has to happen is that the schema language has to document what happens. What could be done, for example, is to take whatever first type matches the value. For example, if you say float union string, then float would have priority, then you make it a float NaN. If string comes first in the union, then you make it a string NaN, right? But then string would always win, of course, if you do it in this way, because anything would be a string. Okay?
Thank you.
But these are very good questions because it means you're already in the design of that. And really, I want you to think not at the level of just learning a schema language, but really learning to understand the design of the schema language itself. Because the sort of questions you ask are exactly the sort of questions that the designers of these languages actually consider when they design the schema language. Okay? All right, so it's a very good sign that you're asking this kind of question. Okay, so true, false. So here is how in JSON schema you could specify some more constraints on the numbers. For example, you can have latitudes and longitudes specifying a minimum and a maximum, right? That would be the polar coordinates. So that's the sort of things you can do. In JSON, you can also do it in the verbose syntax. You can basically add constraints on user-defined types, but I didn't want to overload you with material. Then I told you type can also be array, right? Can be object, string, number, null, Boolean, can also be array. So that's an example. That would be an array of whatever. And if you want to specify what you want in the array, then you have to, that's a static property. It's always called items. And then type, again, a static property. And this is where you plug in the type that you want, right? So this is, as I told you, there's not just a string, number, Boolean, and null. They also added integer, which would correspond to the case where you don't have any decimal point, right? So this is here an example of array of integers. Okay, so that's JSON schema. Hopefully, you realize that JSON and JSON schema are kind of the same. if you want, except for the cosmetic and the documentation and so on, but it's doing the same thing, really. This is the one thing that I want you to see and to be prepared to learn other schema languages later if they come, and you will see it's always the same kind of features. Okay? Who understood that so far? JSON schema? Okay. So now I'm moving to XML schema, but that's only for you to see that it follows the same logic. Like a lot of the things you saw on JSON schema and JSON also apply to XML schema. It's just XML instead of JSON. So let's quickly go through it. Of course, it's very powerful and complex, and I'm not going through everything. I just want to show you the basic things that help you to understand an XML schema. So the first thing you notice, I still use the instance on the top, the schema at the bottom. The first thing you notice is that XML schema is also XML, just like JSON schema is JSON and JSON is JSON. So that's a common thing to do with schema languages. A YAML schema, it would be a perfectly natural thing to define it in YAML, right? So it's the same logic. So now what do we have? Well, you can see that XML schema is entirely static, now that you know the static dynamic thing, because all of the elements that you're going to have in your schema, they are predefined. Just like those that were static in the case of JSON schema, like type, additional properties, these are all static. The same thing goes in an XML schema. All of these elements and attributes are static. Predefined in advance, always the same. So the only thing you can change is the structure and the values that you put in there. So here we have a schema, it's always called schema, and then we define an element that is the name of which is foo, and the type of which is a string. Don't worry too much about that namespace, that is just the namespace in which all of the types are stored. But basically the types that you put in there are exactly the same types as you have in JSON and exactly the same types as you have in JSONic. So there's no surprise there. It's the same list of atomic types. You can just help yourself from that list, right? So that's it. And you can see foo has a string in there that can be successfully mapped to a string. So far, so good. So that's an XML schema. Now I can change it to integer, for example. That's also one in the list that I gave you. So we have an integer. Is it valid? Yes, absolutely. It is absolutely valid because you can parse that. Syntactically, it's just text, right? It's a text node. But you ask yourself when you validate, does that thing here belong to the lexical space of my type? And the answer is yes, you can absolutely parse that as an integer, absolutely. And then when you annotate, that's going to be an integer in your memory, right? So this is what happens. So this is also valid. How about complex structures? Because here we just saw an element with text inside. How about elements with nested elements? So here it's a little bit similar to JSON objects, but just that it's XML, meaning that here we have last and first, and we want strings. So what we say is we define them here, element last and first type string. Here, that resembles a bit the verbose syntax of JSON, right? I told you it's all static in there. So this is why you can only have this, you can only change what you put as the values here of the attributes. And these two you nest into a sequence, that's also a static thing, so sequence, inside the complex type element, also static, inside the element person. So the element called person, that is a complex type containing two elements, last and first, that are strings. Okay, so that is how you define a more complex nesting structure. What you can also do is repeat and control the repetition of elements. It means that you can say, for example, that you want multiple, so 3 of them, you want it between 2 and 4, right? So you have these two static attributes, min occurs and max occurs, that allow you to control. 0 or 1, that's basically optional, right? So you make this one optional. These names are made up. The names that I give here, of course, are totally made up. But min occurs and max occurs, these are the static properties that you need to have in your schema to control the number of repetitions. For whom is that clear? All right. Then you can also say it's empty. Just leave sequence empty. That's fine. You just don't put anything inside sequence. All right. Oh, by the way, I dropped the schema element in here, but that's just not to inundate the slides, right? You obviously always need the schema around it and the element, but I just wanted to stick to the part that changes. That's the reason. It's going to ring very soon. Let's see if I manage to answer your question before it rings.
Does the sequence imply the order of the elements?
Yes, it implies the order. Yeah, absolutely. It is ordered and it has to be in exactly that order. You have a way, another way, but it's not part of the material to make the order optional. It's called all. Yeah. Okay. It hasn't rung yet. Very strange. I'm sure it's going to ring. The minute I try to show you the next slide, it's going to ring. So what you can do is also, if you want to allow for what's called mixed content, you see it's going to, I told you. So after the break, so let's take 15 minutes and then I will finish on the little on XML schema. Thank you.